Hello and welcome. My name is Victor Gijsbers and I teach philosophy at Leiden University in the Netherlands. In this video I want to take a dive into the philosophy of explanation, and I want to talk about three classic theories in that field, giving you a concise overview of what philosophers try to say about explanation. Now, the question of explanation arose in the philosophy of science when philosophers realized that it's very different to, on the one hand, predict something and, on the other hand, explain something. So, if I let go of a stone, it is of course extremely easy to predict that it will fall down. It's easy to do that because we've seen it so many times before, and we never see stones that don't fall when you drop them, unless they are, I don't know, suspended by a rope or something. So explaining that a stone will fall when you let go of it, that's very easy, and people could do that throughout the history of humanity. On the other hand, explaining why a stone will fall down is fairly difficult. It is something that, for instance, Aristotle tried to do with his theory of the four elements, each of which has a natural place. Since the natural place of the element Earth is in the center of the universe, and since a stone contains a lot of this element Earth, a stone will move towards the center of the universe, which for Aristotle coincides with the center of the Earth. I mean, that's a pretty good explanation, which has one problem: it's false, right? That is not in fact how the universe works. And so today we might give a different kind of explanation, one based on maybe Newton's law of gravitation, or even on Einstein's theory of general relativity. So why is it the case that a story like maybe Aristotle's or Newton's or Einstein's can explain something, whereas the, let's say, simple observation that things fall down, especially heavy things fall down when you drop them, can only be used to predict but not to explain? Right? What is it about those scientific theories that makes them capable of explaining something and allow us to understand why it happens? Right? Not just that it happens, but why it happens. So that is the question that these classic theories in the philosophy of explanation try to answer. Now, I call them classic theories in part because they were all developed in the second half of the 20th century, so that's a while ago. But also because the specific kind of theory that I'm going to talk about was more popular then than it is now. And I want to say a little bit about that. So many philosophers working in the second half of the 20th century on questions like these, what they try to do is they try to give us a theory of explanation that is supposed to be entirely general, right? It's supposed to be a theory of what explanation is. All explanation in general, or one theory to fit all the cases. And of course this has something to do with, well, first of all, the idea that a more general theory is better than a less general theory, but also with the idea that as philosophers we're trying to explicate concepts. So here we're trying to explicate the concept of explanation, right? I'm trying to explain what an explanation is. And so there should be a single answer to that, right? If explanation is a single term, a single concept, surely there should be a single analysis. Now, this is a way of doing philosophy that, especially in the philosophy of science, has become less popular over the past 2 or 3 decades. So a lot of philosophers of science nowadays, when they think about explanation, would ask much smaller questions. They would ask about specific types of explanation, maybe even in specific scientific fields. And they would ask, therefore, much more detailed questions that have to be answered by much more local, much more detailed theories. So, for instance, a philosopher of science might wonder how there could be mathematical explanations in empirical science, or might wonder what the relation is between, let's say, a psychological and a neurological explanation of the same phenomenon. Things like that. So more detailed, more specific. And it is less popular to try to give these broad, overarching answers to very general questions like, what is explanation? To some extent, that's maybe good, in part because it gives us a much more detailed view of science, a much more, like a view of science that is much more sensitive to all the differences that are happening in science, which like the classic philosophy of science sometimes didn't really see. And in part it's understandable because it turned out to be very hard to answer these general questions. But there always seem to be some counterexamples, and so maybe we can just be more successful when we zoom in. Now, for me personally, I love the big general questions, and maybe that's one of the reasons why over the decades I've slowly moved away from philosophy of science and slowly moved into metaphysics, because in metaphysics we're still asking the big questions most of the time. But that's fine. So let's talk about these three classic theories in the philosophy of explanation. The first one is going to be Hempel's Deductive-Nomological Model. If you haven't heard that term before, I'm gonna explain it, so don't worry. And then we will look at two alternatives that were developed later on in the 80s or so, 80s, 90s, namely the Causal Theory of explanation and the Unificationist Theory of explanation. But let's start with Carl Hempel and his Deductive-Nomological Model. So here is what Hempel tells us. He says in order to explain something, you've got to give an argument that has as its conclusion the event that you want to explain. Right? So I'm going to give you an argument, some premises, some reasoning, and the conclusion of the argument is therefore, and then there's the event that I'm trying to explain. So the premises show deductively, right, through deductive logical reasoning, that the conclusion had to happen. If the premises were true, the conclusion had to happen. So, I mean, what this captures is the idea that in an explanation, I'm telling you not just that something happened, but that it had to happen. But there are many different ways of thinking about had, right, of thinking about necessity. And Hempel is very much aware of that. So let's suppose that I want to explain why something falls. Let's take a particular event. This pencil, ooh, it fell. Why did the pencil fall? Well, here's one deductive argument. The pencil fell, therefore the pencil fell. That is like logically perfect, right? P implies P. I mean, that's great, but it's not an explanation, right? You can't explain something by just repeating the fact that you're trying to explain. So Hempel wants not just to have a deductive argument, but he wants this to be a deductive argument of a specific kind. It has to be deductive nomological. And here there's the word nomos, which means law. And so what Hempel is telling us is he says what we need in an explanation is we need a law of nature. And that law of nature needs to play an essential role in the deduction. If you take it away, if you take away the law of nature, the deduction no longer works. All right. So the idea is that if I show that something follows from a law of nature, right, then I've explained it. So why did the pencil fall? Well, then I can tell you a story about Newton's law of gravity. And I show you that given Newton's law of gravity and the situation that was here when I let go of the pencil, it had to fall, right? I mean, that just follows logically from the law of nature, and the things that I tell you about the situation is that the pencil falls. So that would be an explanation in this deductive nomological form, which according to Hempel is good. That's what explanations do. They give us laws of nature, and then they show that, you know, given the law of nature, this had to happen. Now, the deductive nomological model was on the one hand pretty popular, but on the other hand, it was also seen rather soon that it runs into a bunch of problems. And I'm not going to talk about all the problems it runs into, but let's just survey a few. So one problem that you might think the deductive nomological model has is, well, maybe it works a bit for some parts of physics, but it's not so clear how to apply it elsewhere. And that's because laws of nature are not that ubiquitous in science. Right? We do not, in fact, in most sciences talk about laws of nature a lot or at all. And this is even true in physics. Right? A lot of physics that you're doing, it's gonna, you know, consist of all kinds of detailed models maybe that we know aren't like precisely true. usually don't involve anything as precise or exact as Newton's law of gravitation. And so it's not so clear that the explanations that we might construct using those models actually fit the deductive-nomological model. And of course, this is going to become much more clear, or much more problematic, maybe I should say, if we move away from physics. I mean, what are the laws of nature that we use in biology? What are the laws of nature that we use in psychology or history or in daily life, where we also give explanations all the time? So that's one kind of problem that Hempel's model faced. Another problem that Hempel's model faced is known as the problem of asymmetry. And here it seems that a lot of explanations have a kind of asymmetry that the deductive-nomological model doesn't. So the classic example is of that where we have let's say, a flagpole and the sun, and because of the sun, the flagpole casts a shadow. And now the idea is that we can explain the length of the shadow by taking the height of the flagpole and the position of the sun, like the angle that the sunlight makes with the earth, and the law of nature that light travels in straight lines. And that works, right? It's beautiful. You say, well, you know, the flagpole is this long, the sun is shining at a 30-degree angle, light always travels in straight lines, and therefore the shadow has to be this and this long. That's great. But what's not so great is that you can also give an explanation that looks basically the same, where you say, well, this is the length of the shadow, this is the angle of the sun, light always travels in straight lines, and so the flagpole has to be this and this long. And now you are explaining the length of the flagpole from the length of the shadow. But we don't really think that the flagpole is, let's say, 4 meters high because the shadow is 8 meters long. I mean, that doesn't seem to sort of work, right? Explanation in this case goes from the position of the sun and the length of the flagpole to the length of the shadow, and not the other way around, right? You could even take the length of the shadow and the length of the flagpole and then calculate where the sun has to be. But that doesn't explain why the sun is over there, right? I mean, only, I don't know, maybe some laws about celestial mechanics and the movements of the planets could explain why the sun is there and not in some other place. So this asymmetry that seems to be there in explanation doesn't seem to be there in Hempel's deductive-nomological model. And that's a bit of a problem. And there are some other problems that I'm not going to delve into right now, such as problems of irrelevance, where it seems that you can use laws to deduce things even though the laws aren't really relevant and so they don't really explain, and so on. It was enough trouble that a lot of philosophers in the 80s and 90s were ready to jump onto some other bandwagon, right? Try some other theory of scientific explanation. And that's where these two rival theories, the Causal Theory and the Unificationist Theory, came in. Now, the Causal Theory starts from what I think is a very intuitive idea, namely that in order to explain something, you need to give its causes, right? In order to explain the length of the shadow, you give its causes, which are the height of the flagpole and the position of the sun. In order to explain the height of the flagpole, you need to give its causes. Well, the sun and the shadow are not among the causes, right? The causes of the length of the flagpole is something like, I don't know, the guy who wanted to buy the flagpole gave an order to the maker of the flagpole. He said, I want a 4-meter high flagpole, and then the maker of the flagpole took a big saw and some story like that, right? It's a story about the construction of the flagpole. That is going to explain why the flagpole has a certain height. Probably. I mean, that seems to be a lot more logical. And so this causal model of explanation tells us that to explain something is to give either a cause of the event, or the cause of the event, or all the causes of the event. Well, and already we're seeing that we're getting into a little bit of trouble. I mean, which of these is it? Right? If I have to give all the causes of an event, well, that's going to be a lot. I mean, do I have to go back all the way to the Big Bang? I'm never going to be able to do that, right? It seems that in explanation we are usually looking for some, like, maybe particularly salient or important causes, and we would need to say something about that, right? What are these salient or important causes? Is that an objective fact? Is it merely a subjective fact about the person who asks the question? So there's a lot of work to be done there. Another area where a lot of work is to be done is in the philosophy of causation. Because once I think that explanation is based on causes, I'm going to have to explain what causes are. Right? What are causes? And that is itself a very difficult question for philosophers to answer, which philosophers of science really jumped on and did a lot of work on. And nowadays, I think a little bit of the same thing has happened, where philosophers of science are sort of asking much more detailed questions, maybe about causation, and it's more the metaphysicians who ask like the big questions about causation. But we can see that like this causal theory of explanation immediately leads to asking questions about causation, which are also extremely important in philosophy and very fascinating. If we'd have to point at like not just more work, but a real sort of problem perhaps for causal theories of explanation, we could point at some situations where explanation just doesn't really seem to be causal. Maybe this is already the case in the example that I gave of the falling pencil. Right? One of the things that we mentioned in that example was Newton's law of gravity. But does Newton's law of gravity cause the pencil to fall? I mean, that seems a little bit weird to say that. It seems a little bit weird to claim that laws function as causes. They seem to have a kind of different role. So we need to talk about that. What are laws of nature? How do they work? That's something that we need to do as philosophers. Maybe more problematic are cases where, well, for instance, I say something like this. Why is the temperature in this room high? And somebody says, well, it's because all the molecules are moving very fast. I mean, that could be an explanation in certain circumstances. I think that could be an explanation, not in all circumstances, but in certain circumstances. Circumstances where somebody perhaps knows about movement of the particles, but hasn't realized that fast-moving particles are the same thing as high temperature. But precisely because they're the same thing, they are not related as cause and effect. Right? I mean, two things that are the same are not a cause and an effect, because a cause and an effect are two separate events. So some explanations seem to work by pointing out identities or other relations like that are not causal relations. And so a theory of a theory of explanation that says explanation is just giving us causes doesn't seem to be fully general. Right? It seems to be the right story maybe about certain types of explanation, but not about all types of explanation. Is that a problem? Well, it is a problem if you want to have a theory of explanation that is fully general, and the philosophers, at this time at least, were trying to get a theory that is fully general. And so that's one of the reasons why not all philosophers jumped on the causal explanation bandwagon, but some of them developed an alternative in the form of the Unificationist theory of explanation. And the Unificationist theory of explanation, basically, like the underlying idea is this. In order to explain something, you've got to show that it falls into a pattern. It could be a causal pattern, but it doesn't have to be a causal pattern. The point is that you've got to identify a pattern that unifies a lot of facts about the universe, so that makes them all fall under a single pattern. And whenever you do that, then you're explaining. And so, for instance, I mean, let's return to our pencil. If I explain the falling of the pencil by using something like Newton's law of gravitation, that's great, because Newton's law of gravitation unifies a lot of different events in the world, like all kinds of things that are falling, but also planets that are moving, and so on and so forth. Newton's law of gravitation unifies a lot of things that you can observe in the world under a single pattern, this pattern of gravitation. And that's why it is explanatory, right? That is why we can use it to explain what happens in the world. And the idea here would be that, patterns can be causal, but they don't have to be. And so there could be other patterns, non-causal patterns, that we use in non-causal explanations. And so the Unificationist theory promises to be more broad than a theory that talks purely about causes. Does that mean that the Unificationist theory is in no trouble at all? No, of course not, because otherwise, it would have been adopted by everyone and we wouldn't have any philosophical discussions about it anymore. Actually, the Unificationist theory runs into some familiar trouble, as well as into some technical issues of its own. So when we come to the technical issues, it's kind of hard to explain exactly what counts as unification. You could say something like, well, if you can take a lot of facts and then unify them as a single fact, right? If you can sort of bring them sort of logically, maybe if I can have a single fact from which all these other facts follow, like logically, that would be a unification. But it's not that easy, right? If I have facts A, B, C, and D, then I can easily construct the fact A and B and C and D, from which all the other four facts follow. But that's not unification, right? I mean, just putting and between things, like the logical and, that's not unification. So when does it count as unification? This is something that actually these philosophers working on those theories spend a lot of time talking about, and it's not easy to make it work. Now, suppose that you can make it work, then the unificationist will still have to show that their theory gives us the things that Hempel's deductive-nomological model didn't, such as asymmetry. I mean, somebody could think that, once I adopt like this pattern of explanation where I trace these sort of straight moving light rays, well, it seems that I can use that to explain the height of the flagpole just as easily as I can use it to explain the length of the shadow. And so if I'm a unificationist, I'll have to tell a story about why one of those comes out as a unification and the other doesn't. And again, it's not so clear how to do it. So one of the authors who did a lot of work on unificationist theories, Philip Kitcher, gave a story that I myself don't think works. Actually, that's part of what my first ever article was about, which was called Why Unification is Neither Necessary Nor Sufficient for Explanation. So there you have it. And other authors, like for instance Gerhard Schurz from Düsseldorf, he basically said, okay, we need to bring in causation at that point. And so you get causation and all the questions about causation back into your unificationist theory. And, you haven't really sort of advanced beyond those problems. So none of these theories is perfect. I do think that a lot of philosophers would tend to agree that maybe not so much the deductive-nomological model with its very narrow emphasis on laws of nature, but surely the causal theory and the unificationist theory capture something of our idea of what it is to explain. Right? I mean, seeing causes and that causes sort of account for effects, that seems to be very basic to our notion of explanation. And this idea that we are looking for patterns and that we understand things better when we see how they fall into patterns, that also seems to capture something about our idea of explanation. But exactly how to bring that together, and whether it's even possible to bring that together into a single unified theory of what explanation is, those questions, well, we talked about them a lot in the 80s, 90s, and we still sometimes talk about them because we haven't really solved them yet.